Welcome to this explainer. Today we're diving into something that is absolutely crucial if you work anywhere near the intersection of data, algorithms, and people. We are unpacking the foundational chapter History of Behavioral Data Science from the Cambridge Handbook of Behavioral Data Science. So why does this matter? Well, if you want to truly understand the roots, the trajectory, and the future of decoding human-machine systems, this is exactly where it all starts. Let's get right into it.
The core problem we're looking at today is massive. Basically, how do we make sense of human behavior in a world driven by algorithms? Think about it. We have mountains of data at our fingertips and incredibly powerful algorithms that can process it all in milliseconds. But human behavior? It remains stubbornly complex. It's nuanced, and it is notoriously difficult to predict or influence if you're just relying on raw data alone.
Here is the roadmap for our intellectual journey today. 1. The human behavior problem. 2. A composite science. 3. Evolution of the field. 4. Real-world applications. 5. Tensions and ethical challenges. And finally, 6. The future of behavior. Starting off with Section 1, the human behavior problem, data versus complexity.
This chapter is a must-read for policymakers, AI practitioners, and business leaders because it hits on a major friction point. On one hand, we've got this modern arsenal of massive datasets and rigid algorithms, but on the other hand, we have human complexity. The chapter brings up a concept championed by pioneers in the space called bounded rationality. Simply put, our decision-making as humans is severely limited by our cognitive constraints and the actual information we have on hand. We aren't perfect calculating machines, right? We use mental shortcuts, we have biases, and our judgment can be completely unpredictable. Because of this bounded rationality, just throwing raw, uncontextualized data at a human problem is never going to be enough. We desperately need a bridge between these two worlds.
Which brings us to Section 2, a composite science, bridging the gap.
The main argument the chapter makes is that behavioral data science is designed exactly to be that bridge. It's not just some isolated discipline operating in a vacuum. Instead, it emerges right at the intersection of theory and method. It's a very deliberate synergy. You take the deep conceptual understanding of behavioral science, and you combine it with the methodological rigor of data science. The result is something entirely new and far more actionable.
To really drive this home, the chapter uses a brilliant analogy. Think of behavioral science as being like abstract mathematics. It's conceptual. It asks the why of human action, digging into our habits, our social influences, and our cognitive load. Data science, meanwhile, acts like engineering. It's methodological. It gives us the how, the statistical inference, the machine learning, the natural language processing. So just as engineering uses mathematics to build physical bridges, behavioral data science uses data engineering to test, scale, and actually deploy behavioral theories out in the real world.
From this composite approach, 4 really key concepts emerge. We just talked about bounded rationality, acknowledging our cognitive limits. Next is the translational space. This is where those abstract psychological and economic theories get translated into testable, actionable models. Then we have human-machine systems. We aren't just studying humans in a lab anymore. We're looking at how humans, algorithms, and complex systems continuously interact in the wild. And finally, expected utility theory. This is an old economics concept about how people weigh risks and rewards, but now it's being mapped against vast, highly complex digital footprints.
All right, Section 3, evolution of the field, from the abacus to AI.
So how did we actually arrive at this highly advanced translational space? The term itself might be new, but the roots go way back. Around 3000 BCE, the abacus laid the absolute groundwork for structured data processing. Fast forward a few millennia to 1936, and the Turing machine gave us the framework for programmable computation. Then we see a massive leap in the 1970s with prospect theory, which successfully modeled human cognitive biases mathematically. By the 2000s, this theory converged with huge amounts of internet data and machine intelligence, unlocking predictive behavioral modeling. And today, in the 2020s, generative AI is shifting us from just predicting behavior to actively simulating it and prescribing targeted interventions.
Let's look at Section 4, real-world applications, behavioral AI in practice.
Because let's be honest, all this history and theory doesn't mean much if it doesn't actually work in practice. Take a look at this number, 6,000. In a really fascinating application in the film industry, researchers used natural language processing to analyze over 6,000 movie strips. They were hunting for narrative emotional arcs, and they found that the man-in-a-hole trajectory, where a character faces and overcomes massive adversity, consistently predicts higher box office revenue and viewer satisfaction. And that was completely independent of genre or budget. It's a perfect example of turning the subjective, messy art of storytelling into a hard, data-driven strategy.
But the stakes can obviously be much higher than box office returns. Look at epidemiological modeling during the COVID-19 pandemic. Using a model called SEIRV, data scientists segmented populations not just by biology, but by behavioral data. By tracking things like contact rates, risk exposure, and compliance using wearable tech, they could simulate actual real-world actions. This dynamic modeling allowed public health officials to craft tailored, inclusive policies for specific at-risk populations, rather than relying on blunt, one-size-fits-all lockdowns.
This field is also incredibly well-equipped to expose and tackle deep societal inequities. The chapter highlights an amazing analysis of 608 U.S. female leaders spanning 2 centuries. The data revealed that Black women frequently have to employ high-risk, multi-domain career strategies just to overcome severe intersectional visibility barriers. Furthermore, the rhetorical focus consistently remains tied to persistent issues like justice and community, which really reflects a long-standing societal neglect of these areas. By quantifying these systemic barriers, organizational leaders finally get the hard data they need to design genuinely supportive and inclusive environments.
Moving to Section 5, Tensions and Ethical Challenges, the Dark Side of Data.
Of course, with this kind of immense predictive power comes a massive amount of responsibility. We have to look objectively at the tensions of collecting data on this scale. The first big one is algorithmic opacity, which you might know as the black box problem. This is the critical lack of transparency in how complex machine learning models actually process behavioral data to make a decision. When an algorithm decides who gets a mortgage or who gets hired, but we can't see the logic inside that black box, accountability completely vanishes. For anyone trying to ensure fairness in AI, this opacity is a constant uphill battle.
Building on that, the chapter outlines a few specific ethical limitations we absolutely have to watch out for. First, there's the risk of perpetuating historical biases. If an algorithm is trained on prejudiced data, it's just going to automate and scale that prejudice. Second, the sheer volume of data collection often leads to massive privacy intrusions, mostly without any meaningful user consent. And fundamentally, there's a philosophical tension here. We run the risk of reducing incredibly rich, nuanced human experiences into mere data points on a spreadsheet. If you're leading an organization today, you need to understand that human-centered ethical design isn't just a nice-to-have. It is a fundamental necessity to prevent data-driven harm.
Which leads us to our final section, Section 6, the future of behavior, ethics, and innovation.
So where do we go from here? The chapter argues that emerging tech is actually going to force us to confront and resolve these challenges. Think about quantum computing, managing impossibly complex variables, or generative AI simulating massive social interactions before a public policy is ever launched. Through all this, behavioral data science maintains its unique position. As the chapter states, it's a hybrid science, conceptual in origin, methodological in execution, and translational in its real-world impact.
As we wrap up, I want to leave you with a provocative question to consider for your own work, your own organization, and the systems you interact with every day. How will you balance the immense predictive power of algorithms with human-centered moral responsibility? Because in this new era, understanding the data is really only half the job. Respecting the human behind that data is the rest of it.
If you want to explore the historical roots, the rigorous methodology, and the ethical frameworks we've touched on today, I highly encourage you to read the full text of Chapter 1 in the Cambridge Handbook of Behavioral Data Science. It is an incredibly rich, intellectually rigorous resource. Thank you so much for joining me for this explainer, and remember to always keep questioning the data.